The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
All right, our first speaker is Dr. Jeffrey Haverl. He's a professor of architecture and associate department head for research at Texas A&M University. He's an ASHRAE fellow and IPMVP fellow. His educational background includes a BS, MS, and PhD degrees from the University of Colorado at Boulder and postdoctorate research at Princeton's University Center for Energy and Environmental Studies. Dr. Haverl has dedicated nearly 3 decades to building energy research at Texas A&M, Princeton University, University of Colorado, Rockwell International, Colorado State, and Colorado State Office of Energy Conservation. Also at the City of Boulder and at the U.S. DOE Administration Services. His work emphasizes statistical building energy modeling, methods for diagnosing operational programs, operator feedback using comparisons of predicted and actual energy use. He is a co-principal investigator of the laboratory's Texas Emissions Reduction Program, the TERP program. You may have heard of that. He does this along with Dr. Baham Yazdani, where he provides technical leadership for code compliance, calculator and emission calculations for energy efficiency and renewable energy. He is the co-principal investigator for the U.S. EPA's National Center of Excellence on Displaced Emission Reductions. He was the principal investigator for the Computer Support and Improved Energy Audit for the State of Texas Lone Star project from 1990 to 2002. This was a $98 million revolving loan fund for the state of Texas to promote energy efficiency. He is a registered engineer of the state of Texas. Dr. Haverl has co-authored 48 publications, 23 books or book chapters, 180 conference proceedings, and 228 reports, and holds numerous U.S. patents. He received a Boulder County Energy Conservation Award, 2 U.S. DOE Innovative Research Awards for work performed at the University of Colorado with Dr. Claridge, a U.S. DOE special citation for his work at Forstall and Germantown complexes, a 1990 GSA Design Award, and a 1992 National Endowment of the Arts Federal Design Award for his work at the Forstall building, and a 2001 ASHRAE Distinguished Service Award. Please help me welcome Dr. Haverl.
Well, thank you, Larry. I'll try to live up to all those things here. So, we're going to talk a little bit today about a number of different aspects of thermal mass. One of the things that I was asked to look into was, how did we get to where we are today with our modeling? So to do this, I had to consult some history books, and I think we'll be able to bring things up to the point where we are today, and then we have several other speakers that'll take you forward into what's possible. Today we've got thousands of new and old buildings. A lot of these are in major cities, and you might want to ask yourself, how are we going to create new high-performance buildings? As well as how are we going to create high-performance buildings from existing structures? When we start thinking about existing structures, if we're going to renovate these structures, How were these structures designed? What sort of design methods were used by the original designers of these buildings? And finally, how did these design methods treat thermal mass or not in some of the cases? Well, today we have pretty much some well-known methods that are used to size buildings, the peak load calculations. They're pretty much split into two different chapters within the ASHRAE handbook. You've got peak heating load calculations and you've got peak cooling load calculations. We also have annual energy use calculations nowadays. And for the most part, this has moved towards a simulation-based calculation procedure. We also have design procedures which are parametrics or coefficients that are based on some sort of simulation. We call those forward methods. And then when we actually get a building built in place and we want to go look at how that building is working, we use a regression typically to try to figure out how that building is working compared to what the expectations are. Those regressions we refer to as data-driven or inverse models. So we've got a number of different procedures today that we work with in buildings to get them built the way we want to. But how did these evolve from, say, 1900 to the present? And how did these different procedures treat thermal mass? Well, if you look at the history of ASHRAE, for example, this is one of the charts that's on their website, you'll notice over time that ASHRAE has evolved. Starting in the latter part of the 1800s, we had a series of organizations. ASHV was one of those organizations in 1894. The first transactions were published in 1895. 1904, ASHV was published, the American Society of Refrigeration Engineers, and there was a bit of ill will between those two organizations in the beginning. In 1905, they published their first transactions, and then in 1915, the Journal of ASHV was actually published, so it moved forward into a journal-type publication. 1922, they published their first guide, so principles that engineers and consultants could use to design buildings. In 32, then the refrigeration and data book were published by ASHRAE. So you can see for a while there were two different paths, refrigeration engineers and the heating and ventilating engineers. Finally, in 1954, ASHV changed its name to ASHA, and then it merged with ASHRAE and ASHRAE into ASHRAE, ASHE and ASHRAE into ASHRAE, and that's what we have today. Now, I realize I'm throwing a lot of acronyms out there, but you've got to remember this when you're going back in time to figure out how a large number of these buildings were built, because they were built with two different societies that didn't necessarily talk to each other. In 1961, finally, the ASHRAE Guide was published, and then starting in 67 through to 2009, our handbooks came out, which is pretty much the embodiment of knowledge coming out of ASHRAE through its technical committees. And that's where you go today to try to find out how to design things. In the early days, prior to the 1900s, there were a series of inventions and a series of theories that were critical to where we are today. Thermodynamics is one of those. Contributions by Carnot, Joule, and Lord Kelvin, Clausius, and Gibbs. Those brought us into the realm where we could start to quantify things that were previously just done experimentally. Heat transfer, Newton, Fourier, we began to have better laws and calculations so that we could actually calculate these things. But remember, in the early days, they didn't have calculators. They didn't have computers either. So typically it was done longhand or it was done with graphs. Weather reporting, interestingly enough. Before we had hourly simulation programs, people didn't think about hourly weather data. They thought about the minimum and the maximum temperatures coming from a particular website. Electricity played a big role as well, as we'll see. And there was a very historic battle between Edison and Tesla that sort of framed the air handling units in the different things that we have in buildings. And of course, the material science, science of insulation, so you've got a spelling error there, metals and welding. None of these things had to take place before we could get to some of the design techniques and construction techniques we take for granted today. And then there were a series of inventions that brought us to the point where we had the tools we could use to go forward. Thermostats needed to be invented, humidity measurements, barometer, vacuum pumps, refrigeration, air handling units, centrifugal fans, steam engines, steam heating systems. In the earliest periods, when we look across the United States, we realized that we do have some idea of how many of these buildings were actually built back in some of these different eras. For example, if we look at the CBEX survey of the United States, which is broken into roughly 4 regions and subsets within those regions, we can see that each of these regions have grown at different rates. Interestingly enough, the vast majority of buildings today, over 50%, are in the South. Okay, excuse me. They were built between 1970 and 1999. Of those, about 40% were built in the South. And you can see that, of course, by the large number of buildings here that started to take off in that period for the South. When we take a look at this data by period, it gives us a way of sort of segmenting the history so we can start to think about the different design methods in the different clusters of buildings that were built during these periods. Pre-World War II, World War II to pre-computer, big change took place when we started to have computers. Early computer use, and then the present buildings, 1990 to the present. So that's how I've sort of divided up the history of things. If we look at where the buildings are, for example, 40% of those buildings roughly are in the South, followed by just short of 30% in the Midwest, about 20% in the West, and only 15% in the Northeast. A lot of people don't realize that, but a large portion of the buildings are in the South and the Midwest, and built during different periods. During the earliest periods, there wasn't a lot of information that a design engineer had at their fingertips to design buildings. One of those things was the Kidder-Parker Handbook, or Guide, in 1904. There was also in 1922 the ASHV Guide that we mentioned before, and in 1932 the Refrigeration Database by ASHRAE. And then finally in 1938 we started to see some manufacturers' handbooks that were published and used as well as the products outside of those areas. So if you look at the suite of things that a consulting engineer in this country had to use, it was rather limited. If we look inside each of these methods, we realized that they were also being driven by changes that were taking place in the computer industry at that time, even prior to 1945. 1800s, 1822 to 1832, Mr. Babbage and Clement produced the first difference engine. Interestingly enough, some of the calculations that they produced were actually used in the 50s and 60s. The finite difference methods came out of some of those early things that Babbage developed. First programmer, interestingly enough, was Ada Lovelace, and she did a lot of the hard work for Mr. Babbage in getting the machine to work. That's his actual computer right there. It's a series of gears and cogs that would spit out numbers. People weren't too interested at that time because they could get the same rough answer with the slide ruler. People didn't realize there was an advantage in moving towards one of these systems. In the 30s then, the differential analyzer became available, sort of a whole room of Babbage's machines. And then finally, in 1946, the first large-scale computer became available. So in this period, we didn't really have that capabilities, but the seeds for the equations that later became the algorithms were started during that period. In 1948, Dr. John Gorey invented his ice machine. There were a number of other people going at the same target at about the same time, but he was credited as being one of the first to come up with a viable machine that actually produced ice. In the late 1800s, there was the war of the currents, interestingly enough, between Edison and Tesla, AC versus DC. And we all know that AC dominated that discussion. But during that period, all the air handling units in their buildings were steam driven until that issue got resolved. So you don't realize that when you're looking toward the turn of the century that we had a change in technology that was hung up on a patent dispute at that point. About the handbook in Mr. Kidder's guide, there was the following statement which I thought was a little bit discouraging, but on the other hand gave us a sense of the state of the art at that point. That there was really no rule by which an architect could determine the size of the furnace used to heat a given building unless you had the specific tables from a specific manufacturer and you were using those tables in your building. So we can see in the early days we didn't really have the early guides that we have today. In 1904, for example, in Kidder's book, you see there was a lot of information on steam radiators. Steam heating systems were fairly common at that point. You picked a particular size of a room. It told you how many radiators you needed for that room, regardless of where it was in the United States. Most things were sized more or less for the middle of the country. When it came to the boiler then, once you knew how many radiators you had, you could size the boiler given the different size and number of radiators that you had. About that same time, interestingly enough, there were some early attempts at air conditioning. One of those was the 1903 New York Stock Exchange by Alfred Wolff. He teamed together with Harold Torrance from the Carbondale Machine Company. They had 300-ton absorption cooling units that were part of a cogeneration system in the building, because they didn't really have enough power at that point to fire up the whole building. It had 42 distribution boxes in the ornate stained glass ceiling of the room, and it actually operated for 20 years until they replaced it. These were similar to systems that Wolff built in the 1890s and early 1900s for the Cornell College and for the Hanover National Bank. He used things, interestingly enough, that came from Germany at that point. Professor Hermann Reichel, 1894, is credited with probably having the first textbook on heating. And he had some mention of cooling, but they didn't know about cooling at that point until Willis Carrier came along and figured out the psychrometric chart. 1904 was one of the first large public exposures to air conditioning at the Missouri State Building at the St. Louis World's Fair. Had a 1,000-seat auditorium in it and about 35,000 CFM of air. And there was a quote in the editors of Ice and Refrigeration magazine. They predicted that the practical application of mechanical refrigeration to air cooling for the purpose of personal comfort no doubt has its field. And the day is at hand, or will soon be, when the modern office building will be incomplete without the mechanical air cooling system. Pretty remarkable quote for 1905. They didn't have the methods at that point, but they were willing to forecast ahead to say that these things were coming. In 1905, Stuart Kramer actually coined the term air conditioning. He was a consulting engineer that was working in textile mills in the North Carolina area. And in 1908, Willis Carrier developed his psychrometric chart in formula. Prior to that, there was no practical way of figuring out how to handle the dew point or how to handle the humidity in the buildings because we didn't have formulas for that point. It was all based on experience. In 1928, the first high-rise air conditioning was built in San Antonio, the Milan building. It was built custom job by the Carrier Company. It was a large office building, about 200,000 square feet, had 11 air handling units, one on every other floor, about another 300-ton system, roughly the size of the Missouri State Building. They didn't know about thermal mass at that point, but they did have evidence that they suspected that a lot of the radiant heat was going to be absorbed by the thermal mass in the building. Unfortunately, they found after building the building and occupying it for the first year that there were big differences between the east side of the building and the west side of the building during the early morning hours in the summer. So they had to split the system down the middle and put diffusers and duct diverters in there so that they could force all the air to the east side in the morning, force all the air to the west side in the afternoon. All that was done manually. This design by Carrier at that point was taken forward in the 30s to install the cooling system in the U.S. Oval Office. There were other things that were done at that point. About 10 years later, Trane actually produced their manual for their company. Inside the load manual, if you take a look at it, there was basic design data. There was construction heat gains. So you looked up different materials from a materials book. You looked up excess solar gains. That's the way they were treating things coming in through the windows. Duct heat gains. Solar temperature difference method was actually part of the excess solar gain method, although it was not a precursor to the solar method that we'll look at in just a minute. As well as on the sheet, they had information about how many people were in the building, how much equipment, what the infiltration was, and that sort of thing. So you pretty much filled out a sheet from the company that was going to sell you the air conditioning system to design a building at that point. So there was no direct treatment of thermal mass. In 1944, that changed. Two professors at Cornell University developed the solar air temperature difference method. That method had a thermal conductance value in it and a decrement factor that allow you to have a difference between the time and the delay as to when a particular heat wave was coming through the wall. So Mackey and Wright in 1944 came up with the soil air temperature method that had a decrement factor and a phase angle that you could begin to compute the effects of the thermal mass. That's more or less what that looked like at that point, if you look at the early journals. It was still very time-consuming and very time-intensive to get these calculations done, but they could be calculated at that point with the slide rule nonetheless. The soil air temperature method was later adapted and tabulated in the ASHRAE Guide and Data Book. That's what this looks like when you look it up in the 61 Guide and Data Book. And within those different methods, following shortly thereafter, was the total equivalent temperature difference method that was based on Mackey and Wright's equations. Within those methods then, for a particular type of wall, you had a temperature difference. So in other words, in trying to actually calculate it, instead of tinkering with the thermal mass, you tinkered with the temperature difference at that point. And it gave you something that looked like that if you plotted those different curves. So there was the appropriate decrement, a decrease in the equivalent temperature difference, and there was a time delay associated with it. So the equations in Mackey and Wright showed up in the ASHRAE Guide as tabulated values in the total equivalent temperature difference method. The guidebooks continued along at that point. There were a series of them. Train and Carrier now were producing guidebooks. ASHRAE continued with their guidebooks, as well as the handbook starting in '67, which began to contain not only the tabulated values of the Mackey and Wright equations, but the appropriate weather data to go with it. So you could begin to get some certainty that two engineers might possibly have a system that's similar in the same building if they compare their designs. Further along that line, if we take a look at the actual peak cooling load calculation, the total equivalent temperature difference method based on Mackey and Wright was tabulated by Stewart in '48 into the tables that showed up in the handbook. And as I mentioned earlier, thermal mass actually showed up as an adjustment to the temperature difference in the peak load calculations. Later, in 1974, two authors, Rudoy and Duran, took this idea and decided to replace the total equivalent temperature difference with a new type of calculation, one based on response factors that would give them a more accurate calculation. And that is what showed up in the 1977 ASHRAE handbook. This procedure actually ended up with a substitute series of variables there. So instead of having a UA temperature difference, you had a UA cooling load temperature difference. Windows then had a shading coefficient, solar heat gain factor, and a cooling load factor. Internal lights, as well as people, had cooling load factors so that you could link them to the thermal mass in the building. So each of these then began to give a little more accurate representation. Those were tabulated in the ASHRAE handbook and gave you a series of calculations that you could walk through. Then using superposition or simply adding those temperature differences and delays, you get some idea of how the building was functioning. This is what they looked like in the ASHRAE handbook in 1977. They were later modified by Ed Sowell through simulation, ASHRAE Research Project 359, who went ahead and ran several 100,000 simulations so that they could update those with a better set of calculations. These were continued to be modified with a new set of conduction transfer functions by McQuiston and then by Spittler and McQuiston in 1993, where they devised a yet even better set of cooling load factors. So the same principle of these ideas has moved forward to today. Other developments at that time were the finite difference, finite element method. These were early calculations for solving the RC networks. They weren't very eloquent at that time, and so they were available, but they weren't looked upon by the academics as something that was publishable. Over on the other side of the Atlantic, the Chartered Institute of Building Service Engineers, CIBSE, used the admittance method in some papers that were developed in the 60s to calculate the time lag for thermal mass. Annual energy calculations up through the years have used a degree day method for heat load calculations and equivalent full load hours in the early periods. These gave way to bin methods and modified bin methods, which were in the just up until the most recent handbooks within the ASHRAE literature. These essentially took the weather data and binned it into temperature bins, and then you multiplied each of those bins times an expected building performance of the building under those different temperature characteristics. They could be used for either heating or cooling loads, and there was an adjustment for the thermal mass within the temperature bin method, the modified temperature bin method. In this period, there were some fairly dramatic improvements in the computers and the algorithms and the programming languages that were used for that. Beginning with Fortran, which was one of the first transportable codes, aside from assembly language, that allowed you to write a program in one manufacturer's computer and transfer it to another computer. That's evolved up to Fortran 2008 today. In the early days, you had mainframe computers, or sort of the early version of not exactly a personal computer, but the PDP-1 was the precursor to the personal computer, which has, of course, evolved into the iPods and iPads that you see today. I think the new iPad is out, I think. Yes. The first thermal network, interestingly enough, which is the basis for all of our simulations today, was published by some undergraduate students at MIT in 1944. It evolved over time. There were a number of different things that were changed, reference temperatures, that sort of a thing. ASHRAE actually sponsored a research project which investigated this a little bit further. The exterior walls were represented by multi-layered RC networks. They had a radiation network on the interior of the wall. This is what the analog computer looked like that was used to solve it. It was not really a computer. It was a patch board of resistors and capacitors. The results then were displayed on the oscilloscope right here, and to get a sense of the thermal wave going through it, you took a snapshot, you took a photograph of the oscilloscope, and then you could see how the heat wave was moving through the wall. What took place in an hour to 24 hours took place in less than a 60th of a second on the oscilloscope. So there was a bit of a time difference there. But that principle is the same principle that we're using today to simulate things. So the thermal mass networks in the 50s moved forward into today, into our computer algorithms that we use to solve things. And as I said, they had multi-layered walls even in the 50s. They used nodal temperatures or lumped capacitance to represent things, solved first by analog computers, and viewed the results on the oscilloscope. The computer algorithms took this idea of a heat balance and used it to move into the realm of computer programs. But they needed a method of solving the dynamic heat effects that was not based on finite differences. That came along with Stephenson and Middleus in the 60s. Their work was based on work by Briskin and Recht, who were engineers at the General Electric Company in the 50s, and later by Hill, who was at NACA, which is the predecessor to NASA in the 50s, who was looking at airplane skins. The thermal response factor method was actually a method of representing the time-varying function of heat moving through different media by a different set of pulses. Okay? The original set of pulses that Briskin and Recht used were rectangular pulses. Hill used a triangular pulse, which is what was adopted by Middleus and Stephenson, and is in use today in almost all of our computer simulation programs. The CLTD, CLF tables that I mentioned to you earlier that replaced the total equivalent temperature difference tables used pre-calculated values for 40 degrees north latitude using the thermal response factor methods that were out of Middleus and Stephenson. These have graphically, they look something like that. So in other words, they found that if you have a sinusoidal wave right here, each of the different points on that wave could be represented by a triangular pulse. The computer algorithms evolved over time into the programs that we've got today. This is some of the programming logic, for example, for the DOE2 program. It's a weighting factor method. There's a lot more algorithms here than I can display on the screen, but this gives you some idea of the clustering of the algorithms. Over time, this work began in earnest in the latter part of the 60s and continues today. These programs have, let me just back up here for a second. These programs have evolved to the point, I'll show you in a minute, where we actually now have a merging of some of the different subroutines and the codes into the latest version of programs. At the same time, in the early development of some of these programs on the mainframe computers, we still had a continuing progression of books that were coming out. Guidebooks, handbooks, as well as the 1975 ASHRAE Task Group on Energy Requirements, or TGER, TIGER as it's known, that actually published the algorithms inside of some of the basic programs so that they could be rewritten into microcomputers by others not associated with the large mainframe computers. In the guidebooks as well, you saw similar sorts of things, both in the fundamentals and updating constantly in the train air conditioning manuals. Last but not least, in the last couple of years, we've seen a revision to the response factor methods by Spittler and Fisher, two professors at Oklahoma State University, and Kurt Peterson, retired professor from University of Illinois, in the radiant time series method that actually resolves some of the intricacies of the radiant heat transfer with the coupled convection heat transfer inside of the zones. That's now making its way into the 2001 ASHRAE handbook, in the 2009 ASHRAE handbook, but unfortunately it's no longer something you can do by hand. It requires software now. So we've almost moved completely out of the realm of hand calculations. That was extended into the residential methods by Barnaby, together with Spittler and Zhao in 2004, again appearing in the 2005 ASHRAE handbooks. It does require a computer now to use these methods. Last but not least, and I think some of our other speakers will be talking about this, we've had some new developments that have shown us a way forward where thermal mass in the building wasn't just the thermal mass in the structure or the envelope, but it's actually thermal mass that's embedded in the heating, ventilating, air conditioning, and refrigeration system. And I'm speaking in particular of heated cooled slabs. These will probably become the replacement for the air handling units, air handling unit driven systems that we have today. The reason why is the delivery efficiency is so much higher for heated cooled slabs. It requires a completely different way of designing the buildings, and it requires a new set of simulations, some of which is beginning to come out in the Energy Plus and Trinza software today. So over the years, we've had a series of families of software that have started in the 60s. The DOE2 program, which is culminated in the eQuest, the free software that's available on the web, which is probably the most widely used computer program outside of the programs that the train and carrier company offer. We've had the building loads and system thermodynamics program, the BLAST program, which is combined with the DOE2 program into the Energy Plus program today. We have the Trinza series of programs at the University of Wisconsin, the train trace programs, and then finally the carrier HAP programs, bringing us up to today where we've got the latest version of a series of these competing programs. All of these programs use the response factor method, the transfer functions, which go back to the work in the early 50s based on the first calculations on the analog computer and then working their way into computer algorithms. There are lots of thermal mass studies, and I'm not going to list them all. I do have a report at our laboratory that we'll be publishing that's a more detailed analysis of this. These are some examples of that. We're looking now into thermal structure factors for thermal mass, as well as thermal mass factors, which are part of the ASHRAE standard 90.1. And then, of course, radiant heating and cooling, which has become sort of the system du jour within a lot of the ASHRAE literature lately. So all of this works its way out onto a timeline like this, and I realize you can't see it, but you can see that there's a lot of stuff on here. So when you talk about the history of thermal mass, you realize it's integrated and it's woven with a number of other different fields about how it's evolved to where we are today with things. So in summary, it's important to consider the building stock for the last 110 years because many of those buildings that are around today were built some time ago. We're tied with the changes in the professional societies as well as the computer programs and some of the previous developments in heat transfer and thermodynamics, which led to the kind of a revolution that took place in the 50s and 60s. From 1904 to 1938, there was really no direct consideration of thermal mass in buildings. Starting in 1944, the paper by Mackey and Wright, together with the solar air temperatures, allowed us to start to think about thermal mass. That, together with other developments at that time, refrigeration the AC/DC battle, which got resolved, the psychrometric chart by Willis Carrier, and then finally the coining and the use of air conditioning systems, both in the New York Stock Exchange and other buildings like the Milan building in San Antonio. Total equivalent temperature difference was a tabulation of the original Mackey and Wright equations. That gave way to the cooling load temperature difference, cooling load factor method in the 60s. Annual calculations have moved into the modified bin methods where they have sort of stopped today. And our computer programs today are based on some of the early programs in the 1950s that began with analog computers. So we've gone through response factors to radiant time series, and finally some of these new transfer functions that are starting to look at the actual radiant heating systems within the HVAC systems. Questions?
Please use the microphone here so your question can be captured online as well. Please come to this microphone. We have time for one question.
In the masonry industry, we're particularly interested in the heat flow through the wall and how the mass affects the impedance of the wall to heat flow on a daily basis. Is there any software out there that can do that? I'm assuming it requires a finite element model of the wall itself.
There is a lot of software out there that can do that, and ASHRAE actually has a standard 140, which is a method of test of software. So if you're looking for a particular software package that can handle the appropriate dynamic effects of the thermal mass, you want to have a package that's been run through the rigors of the standard 140. So yes, there are many, and they're listed in the presentation where I showed you the whole family of software packages.
And you'll be able to access the presentation online in the future from ACI's website. Thank you very much.